Hello everybody, welcome to the course VLSI Design Flow RTL to GDS. This is the 12th lecture. In this lecture, we will be going through RTL synthesis. In the earlier lectures, we had seen that the logic synthesis consists of various smaller tasks. For example, the RTL synthesis, then logic optimization, then technology mapping, and then technology dependent optimization. So, the first part of logic synthesis is RTL synthesis, and in RTL synthesis what do we do? So, we basically translate the given Verilog code or the RTL model into a netlist consisting of generic logic gates. So, this is the responsibility of RTL synthesis. So, the RTL synthesis is also a complicated task and we further break it down into smaller tasks. So, the smaller tasks are parsing, elaboration, and then translation of various Verilog constructs in the code to the logic gates, and also some optimizations which are RTL construct specific. So, in this lecture we will be looking into the parsing and elaboration and the translation of some of the important Verilog constructs, and in the next lecture we will be going through the translation of more Verilog construct and also look into the optimization which are specific to the RTL model. So, the given an RTL code or an Verilog model representing an RTL, the first task that is done by the RTL synthesis tool is to read the given RTL files and populate a data structure for further processing. So, in the earlier lectures we had seen that the Verilog code consists of various it consists of characters, and characters can be grouped together into tokens, and we have various types of tokens, for example identifiers, keywords, operators and so on, right. So, the given an RTL file and a Verilog code, so the first task that is done by the tool is known as lexical analysis. So, the lexical analysis basically breaks down the given RTL code into tokens, various kinds of tokens, for example keywords, identifiers and so on. And after this lexical analysis, it checks for the grammar of the given code, whether it is following the prescribed syntax and syntax of the Verilog language, and if there are say errors, then in that case the tool will report syntax error in the code if the given code doesn't follow the grammar of the Verilog language. But if the given RTL code is syntax error free, meaning that it is following the grammar correctly, then what the tool will do is that it will build an data structure which is typically a kind of syntax tree or a parse tree, and this is a kind of hierarchical data structure. So, by hierarchical data structure we mean that if some object RTL construct contains some other RTL construct, then the parent child relationship is maintained and so on. So, that makes a kind of a hierarchical data structure, or that based on the parent child relationship, a hierarchical data structure is built for the given Verilog code. So, let us take an example that how it is done. So, suppose we are given or the tool is the RTL synthesis tool is given a Verilog file in which there is a module say top, okay, and for simplicity we are not showing the internals of this top module, and there is another module say mid, and it contains an always block and so on. Now, for this code, what will be the syntax tree, or how will that syntax tree look like? So it will be something like this. So there will be at the top there is a root, right? And so Verilog is in Verilog, the module is the topmost entity of design. So there will be the root will have as children various modules. So in this case there are two modules, top and mid. So those will become the children of the root. And then the in mid we have in the given code we have an always block. So always block is contained within mid. So the always block will be a child of the module mid, right? And then within always block there are three statements, right? We have three statements. So each statement will form one child, right? So there are two non-blocking statements, right? These two are non-blocking statements, and those will become a non-blocking state. So two child will be created corresponding to those non-blocking statement, and one child will be created corresponding to the blocking statement, right? Now each statement has an LHS and RHS, right? So this non-blocking statement will contain LHS part and the RHS part, and so on. So this is how the given Verilog code will be parsed, and a data structure will be built, a hierarchical data structure. And then once this hierarchical data structure or parse tree is built, then the RTL synthesis tool goes to the next step. And what is the next step? The next step is called elaboration. So what is done in elaboration? So in elaboration, the RTL synthesis tool checks whether the connection among the RTL specific components are legitimate, right? So we'll understand what do we mean by legitimate connections, okay? And if it is legitimate, then during elaboration the connections are made in the internal model that is used to represent the given Verilog code, okay? So let's take an example. Suppose there was a design in which we have, say, one module leaf, right? This is a leaf level module, and then there is another module middle, right? There is a module middle which contains an instance of leaf, right? So this is an instantiation of leaf. So the leaf is, we say that for this instance F1 is the name of the instance, the master module is a leaf, because the name here is referring to this other module. So the master module of this instance F1 is leaf. And then there is another module, say top, and inside top we have three instances, two instances of leaf, right? So I1 and I2 are the instances with master module as leaf, and I3 is an instance whose master module is middle, this one, right? So this is the given RTL code. If we give this code to the RTL synthesis tool, then during elaboration the linkages between the leaf level module, sorry, the instances and the master modules are made. And in this instantiation, if there are some problems of connections, then those problems are reported and as elaboration error. For example, if we say that the master module is leaf, and in leaf we have three ports D, clock and Q, right? And here we have written D, clock and Q. So here there is no problem. But suppose we made an error, and instead of writing D here, we wrote here D1, right? So this kind of error will be reported by the RTL synthesis tool during elaboration. So when initially the RTL code is read, at that time there is no linkage is created between the instances and their master module, right? So those during the initial stages the code is read module by module. So at that time the tool doesn't know that what is the direction of the input, this pin D, clock and Q and so on, right. So, the tool can actually make a some simplistic assumption initially. So, for the leaf level module, level module leaf, the tool can understand that the direction of input pin is D, input pin D, the direction of port D is input, it will be creating. For the clock it is input, for Q it is output, right. But when it will create the module middle, it will take an it will process the instance F1, right. So, it will create an instance F1, but while processing this module, the tool will, before establishing the linkages between the instance and the master module, it does not know that what is the direction of this pin D, this pin clock and this pin Q. So, the tool can make some simplistic assumption like treating all of them as input pin, right. Similarly, in the module top there are 3 instances, or 2 of leaf and 1 of middle, right. So, when the tool is analyzing this particular module top, at that time it does not know that what are the directions of these pins D, clock, Q and so on, and it can make a simplistic assumption that all pins are input pins, right. And after elaboration, what it will do is that it will create linkages between this instance and the master module, this instance and the master module, and this instance and the master module, and then a design hierarchy will be built and the connections will be also be created. So, let us understand that after elaboration what will happen. So, this was the view of the design when no elaboration was done. So, in this case what we see that the modules are separate. So, the all modules and instances are totally separate, but after elaboration those will be linked together. So, now at the top level, so this is the top level module. In this top level module we have 2 instances of leaf with name I1 and I2, and now the directions of the pins are inferred from looking into this master module of leaf, and the direction of pin D will be taken as input, for pin clock it will be taken as input, and for the pin Q it will be taken as output. Similarly, the correct direction will be inferred, and then and a design hierarchy will be built, and also the connections will be made, right. Now, during this stage there can be errors or elaboration errors that the tool can report. Now, when can the error be? So, there are some common situations. Suppose while we are running the logic synthesis tool or RTL synthesis tool, and we gave and these three modules were in separate Verilog file, and by mistake we gave only these 2 files and forgot to give this file, right. In that case, the tool will not be able to establish that what does this module leaf is, right, because the master module of the instance F1 is leaf, and we have not given the module corresponding to leaf by mistake, right. So, if we make such kind of mistake, then the tool will not be able to establish the linkages between the instances and the master module, and as a result what it will happen is that it will the tool may report an error. It will report an error that there is no reference of module leaf in the RTL files, and therefore, it is assuming leaf to be a black box, right. Now, this is a situation which we encounter commonly in logic synthesis, and it means that probably we have not given the reference of, or we have not given the module which contains the description of the module leaf, right. So, that is one mistake that can be made or that can be reported during elaboration, that the black boxes in our design, right. So, typically there should not be a black box in our design. Otherwise, even the direction of those pins cannot be inferred for their instantiation, and then the tool can behave unexpectedly. So we should look into the warnings or errors corresponding to black box in our design carefully. Then other kind of errors can be with respect to the port names. For example, if we make error in the name of the ports while instantiating, then in that case that problem will be reported during elaboration, or there is a mismatch in the width of the buses and the pins in the instantiation, then the tool can report error. Okay. Another responsibility of elaboration is that it processes parameterized module. So, in earlier lectures we discussed that Verilog supports parameterized modules, meaning that we can have parameters in our module, and based on the value of the parameter, the module can have different interfaces. For example, the width of a bus or a port can change based on the parameter, and the parameters value can be different in different instances. So, in that case, what the tool will do, the RTL synthesis tool will typically do, that it will create separate modules with different interfaces for each distinct set of parameters. Okay. Now, what it means, let us look into an example and then we will understand. So, suppose there was a parameterized module counter with a parameter width with a default value of 4, right, and there is an output port with the name count, and its size depends on the value of this parameter width, right. So, if the value is default value, then the output port count will be treated as count 3 down to 0, right. It will be 4-bit wide, right. Now, during instantiation, we can change the value of the parameters. For example, in this instance C1, we are not changing. So, in this case, the default value of 4 will be used for count 3, right, for the instance C1. For the another instance C2, we are saying that instead of 4, use a value of width as 8. So, in this case, the width of the bus, so width of the port count will be 8 instead of 4, right. And similarly, in the third instance, for the C3, we want the width to be 16, right. Now, in this case, what the tool will do, it will internally create 3 different modules, one for width 4, another for width 8, and third one for width 16. So, how will our design look like? It will look like something like this. So, for the instance C1, the count will take a value of 3 down to 0, or it will take a width of 4, for C2 8, and for C3 it will be taking 16, right. Now, what will be the name of this new modules that will be created during elaboration? So, it is tool specific. Typically, it will use a combination of the name of the parameter and its value. So, it may be say count, the master module name initially was say counter. So, in this case, during elaboration, the new module will be created and its name can be counter underscore width underscore 4. For this module, for the other it can be counter underscore width underscore 8 to denote that the value of the width is 8 and so on. But note that this name is the name of the master module that will be created by the tool. It is tool specific. The tool is free to choose any name. Before going through various RTL constructs and understanding how they are synthesized to logic gates, first let us understand that which RTL constructs are or Verilog constructs are synthesizable and which all are not synthesizable. Why? Because some Verilog constructs are there which support other design tasks such as functional verification, and those are not meant to be synthesized. right. So, a given RTL synthesis tool may not support all synthesizable Verilog constructs, right. This is also a point that should be noted, that there is no, the language as such does not say that what is synthesizable and what is not synthesizable, right. So, the it is very much tool specific, that which RTL construct is supported by that tool for synthesis, and which constructs are not supported by the tool. And therefore, as a designer, we should be aware of the Verilog constructs which are supported by the synthesis tool that we are using, and then write our Verilog code and so on in taking that into account. So, there are some RTL constructs which are typically not supported by RTL synthesis tool. So, let us understand or take a look at them. So, the first thing we should note is that the delay specification. For example, if we write a statement out1 which is assigned to A after a delay of say 12 time units. So, this kind of delay specifications are not supported by synthesis. So, these delay specifications are typically useful for simulations, right. In the simulations, we want to understand that the Verilog code, or we want to verify that whether our RTL model behaves correctly when there is a delay of say 12 time units, right. So, the hash delay kind of constructs, if it exists in the RTL code, it should be interpreted as that this means that this delay is meant to simulate and see that what happens to our RTL model if this much delay happens, right. But it is not meant to say to the synthesis tool that insert a delay element which has a value of 12 time units, right. So, the delay is typically what the synthesis tool will do is that in these cases the delay specification, for example, the hash 12 in this case will be totally ignored. So, the RTL synthesis tool will treat the statement as out1 is assigned to A in a non-blocking manner, that is it, right. So, the hash 12 will be totally ignored. Okay. So, there are other RTL constructs which are not supported in synthesis, for example, initial blocks. So, initial blocks are useful in writing test benches that we have seen earlier, right. And then there are fork, join, force, release, and data types real and time. These are not supported for synthesis. And there are system tasks, for example, $display, $monitor and others, those are not supported by the RTL synthesis tool. So, these system tasks are useful in verifying our design or doing functional verification or simulation. Now, let us look into the RTL constructs which are synthesizable and how they will be synthesized. So, first let us look into the assign statement, right. So, the continuous assignment statement. So, how is a continuous assignment or assign statement synthesized if it exists in the RTL code. So, corresponding to the assign statement, a combinational circuit will be inferred. And what combinational circuit will be inferred? It will depend on what is on the RHS of the assigned statement. So, let us take an example and understand this. Suppose there is a module top, and in which we have say 3 assigned statements. So, the first assigned statement says out1 is equal to A and B or C, right. So, this is the RHS of the assigned statement, and the logic will the RTL synthesis tool will instantiate logic gates corresponding to the RHS. So, it will be something like this. So, for the output port out1, right, it will be an AND and an OR gate will be instantiated corresponding to these operators, these logical operators. Similarly, for out2, since out2 is of size 4, right? It is a bus of size 4. So in this case, and x and y are also of size 4. So when we assign out 2 is equal to x and y, there will be 4 AND gates that will be instantiated, right? So x0, y0 will be ANDed, and out 2 0 will be driven by that, and so on. And for the third one, out 3, we have a ternary operator. So when S is true, then Q, the out 3 takes a value Q, otherwise it takes a value of P. So this is a description corresponding to a multiplexer. So the tool will instantiate a multiplexer in which S is appearing on the condition, right. So the S will be on the select line and P and Q will be on the data line. Now let us look into how the statement if else will be synthesized by the RTL synthesis tool. Now if else is a kind of a multiplexer kind of thing, meaning that if something happens, then one line will be selected, otherwise some other line will be selected. So corresponding to if else statement, a multiplexer will be instantiated in our design, and the select line of the multiplexer will be corresponding to the condition that appears in the if condition, right. So let us take an example and understand. So let us say let's look into this always block, right. In this always block, there is an if else statement. Now if S is equal to 0, right, S is equal to 1 tick P 0, that is S is equal to 0, then out 1 is equal to A, right. If S is 0, then out 1 is equal to A, else out 1 is equal to B. So corresponding to this, a multiplexer will be created, right. So out 1 will be driven by this multiplexer. On the select line we will have S. Why we will have S? Because it is coming in the if condition, right. So here we have the select line, and when a select line takes a value of 0, then A is driven to the out 1 port, right, and as described as represented in this RTL code. And if out 1 if S takes a value of 1, then B will be driven to the output port, right. So this is with the how the an if else kind of RTL construct will be synthesized by the RTL synthesis tool. Now how will the case statement be synthesized? So the case statement will also be synthesized into a multiplexer or a select logic. Select logic is inferred. So the size of this multiplexer will depend on what is the complexity of the case or the signal appearing in the case statement, which is selecting various values, right. For example, in the suppose we have a case statement like this. Case statement is like this. So in this case statement, we have the selection is based on the signal S. And what is the size of S? The size of S is of 2 bits. So in the multiplexer that will have 2 lines on the 2 bits on the select line, right. So this kind of case statement will basically translate into a 4 to 1 multiplexer, because there are 2 select lines S0 and S1, right. And if these two take a value of 0 0, right, then line A will be selected, right. If they take value of 0 and this one is 1 and this one is 0, then B will be selected, and so on, right. So this is how the case statement will be selected, right. Now in a case statement, Verilog supports that there can be multiple matches, right. So if we write say question mark or don't care conditions, in that case there can be multiple matches, and in that case what will the behavior of the Verilog code? It will be that whatever matches first, that will be selected by the case statement, right. That is what is defined by the language, and therefore if there are multiple matches in the case statement, then the tool will infer or instantiate a kind of priority logic, right. So let us take an example and understand it. Now, suppose the code is like this, the case statement is like this, right. Now, S is again of 2-bit, it is a 2-bit line, right. Now, how many possibilities are there for this signal to take, right. So, it can take 0 0, 0 1, 1 0 and 1 1. So, what we are saying is that if in or what this description says, that if one question mark means that this can take any value 0 or 1, out 1 takes a value of A, right, meaning that if it is 1 1 or 1 0, in both these cases a value of A will be driven to the output, right. And then what the second line says, that if it matches either with 0 1 or 1 1, it should out 1 should be driven to B. But note that the case 1 1 is already covered in the first case, right. So, it cannot match in the second case, right. So, only 0 1 case will take a value of B, and then default is D 0 0, and in the 0 0 case out 1 will get a value of C, right. So, now we have to instantiate logic gates such that this kind of priority is maintained in the logic structure or in the implementation or the circuit. So, let us look into how the instantiation will be done. So, it will be something like this. So, if what we have here is that if S1 takes a value of 1, right, if S1 takes a value of 1, then out 1 gets a value of A, right, it will get the value of A. This line will be totally ignored, right. So, what it means is that if the value of S is 1 0 or 1 1, in both cases out 1 will get a value of A. So, this is what we wanted our priority to be, right. Now, if it does not match it does not get the first or it does not match the first statement or first condition, one question mark, then it goes to the next statement, and in that next statement what it does is that it looks for S1 in the S0 or the lower bit, right. So, if S0 bit is 1, then B will be selected and it will be going to out 1, and if S0 is 0, then C will be selected and to the out 1. So, the required priority that we wanted to have in as described in this RTL code, that is maintained by this circuit, right. So, this kind of priority can also be enforced by if else if kind of construct. In that case also a priority based logic gate structure will be implemented in the netlist generated by the RTL synthesis tool. Now, let us take a few examples of an always block and then understand that how always block will be synthesized. So, first let us take a few examples for the case when the always block is edge sensitive, right. So, let us consider this module D flip flop. So, in this module we have an always block in which is sensitive to the clock signal clock, and whenever a positive edge to the clock signal appears, then whatever is there on the D, that appears on the Q or that is assigned to Q, otherwise Q retains its old value. So, this is a description of a D type flip flop, and for in this module will the RTL synthesis tool will basically instantiate a D flip flop as shown here, right. So, whenever a clock's positive edge appears at the clock, whatever is in the data that will be propagated to the Q pin and it will appear at the port Q. Now, let us take another example in which the always block is sensitive to both clock signal and the reset signal, right, and it is sensitive to pause edge clock and neg edge reset. So, when reset takes a value of 0, then Q is assigned a value of 0, otherwise Q is assigned a value of D, right. So, note in this case that this clock and reset, these two signals can appear or independent of each other, right, and therefore, this is a kind of, this reset signal is a kind of an asynchronous reset, meaning that it can come anywhere during any time of the clock period, and it can reset the flip flop, right. So, corresponding to this description, flip flop will be instantiated in which there will be an asynchronous reset pin, and there will be, it will be it is sensitive to, or reset is active when it takes a value 0, and therefore, we will have a bubble here, meaning that when reset is equal to 0, then Q will take a value of 0, right. Now, let us take another example of an always block, which is sensitive just to the clock signal. So, this always block will be triggered only when pauses clock appears, right. Now, but when it enters, it looks for first the signal reset, and if reset is equal to 0, then Q becomes 0, right, otherwise Q takes a value of T, right. So, once the clock edge comes, then it looks whether that D pin what is the value of reset. If reset is equal to 0, then Q becomes 0, right. So, it is a kind of a synchronous reset kind of thing, right. So, we can all look into this part and consider it as a multiplexer, right, and therefore, a circuit like this can be inferred by the tool, right. So, there is a flip flop, right, this flip flop, and the D input that is coming to the flip flop, it is either 0 or D, because this if else statement corresponds to a multiplexer that we have seen earlier, right. So, if reset is equal to 0, then this line will be selected on this line we will have a 0 constant value assigned to this multiplexer, and then if the reset value is 1, then whatever is D that appears on the, or the D port that appears at the D pin of the flip flop, right. So, now this is how this module or this RTL construct will be synthesized, right. Now, the tool RTL synthesis tool can further optimize it. For example, instead of using a multiplexer, it can use an AND gate or so on, right. So, whatever we are discussing in this lecture, the tool may instantiate some other logic gates also, right. So, you should note this point, that what we are showing in this slide, the tool may instantiate some other logic gates also, but whatever the tool will instantiate, it will be functionally equivalent to what we are discussing in this or showing in this slides. So, instead of say multiplexer, the tool can always instantiate an AND and OR gate, and then and so the exact implementation of the RTL construct is dependent on the tool, right. So, for a given Boolean function, tool can implement it in many different kind of ways, but the meaning of, based on the meaning of the Verilog construct, the tool will always generate a circuit which is functionally equivalent to what we are discussing in this lecture. Now, the always block can be synthesized in different ways depending on whether we are assigning a signal in a blocking manner or non-blocking manner. Okay. So, let us take an example and understand it. So, the another important point that should be noted is that the Verilog language as such was invented for the primary purpose of simulation or verification, right. So, Verilog, you might remember that Verilog language or the word Verilog was derived from verification and logic, right. So, the initial purpose why Verilog was invented was for verification using simulation. So, the syntax and semantics of simulation was very well defined initially, and then later on the Verilog language was used for the synthesis, logic synthesis, RTL synthesis purpose. So, later on when RTL synthesis tools were developed, they use the same syntax and they followed the semantics of the simulation that was being followed in the synthesis also, right. So, the handling of blocking and non-blocking assignment in always block is done differently. How it is done? It is done in the manner such that it is consistent with the simulation, right. That is what what is an important point to note. So, once we understand that what is the how things will be simulated, then the synthesis tries to mimic that thing, right. So, let us take an example and understand it. Okay. So, suppose this there is an always block in which there is a clock signal. It is so this always block is triggered by whenever pause edge appears at the clock signal. So, whenever now in this always block, all the assignments are in a blocking manner, right. So, it is similar to a programming language. The first statement will be executed, then the second, then third and fourth in sequence, and all the statements will be executed. When one statement is executed, the others are blocked and so on, right. So, in this case, whenever the clock signal pauses clock appears, then whatever is it at in1, that will be assigned to reg1, and then whatever is at reg1, that get assigned to res2, and then whatever is at res2 that gets assigned to res3, and whatever is at res3 that gets assigned to out1, right. So, all these assignment happen at a single clock edge, right. So, in effect, whenever the clock edge pauses clock edge appears, whatever was at in1, that appears at out1, right. So, in effect, this res1, res2, res3, these are redundant, right. These are not so, in effect, what this always block is doing, whatever is at in1, that is passed to out1 in whenever the clock edge appears, right, because all these statements are executed in sequence, and as a result, finally what happens, that out1 gets a value of in1. So, in this case, the tool will instantiate only one flip flop, and the D pin will be connected to in1, and the Q pin will be connected to out1, right. So, this is how the tool will synthesize this always block. Now, let us take another example. Now, in this example, everything is same, only thing difference is that we are using non-blocking assignment, right. Now, remember from earlier discussion that the non-blocking assignment is executed in two steps. In the first step, whatever is on the RHS, that is evaluated and scheduled to be assigned to the LHS later on at the end of the simulation, right. So, what happens in this case, whenever clock edge appears, positive clock edge appears, so whatever was the value of current value of in1, that is assigned to reg1, right, that is not assigned to reg1, but that is scheduled to be assigned to reg1, right. That is an important point. The value of reg1 is still the old value, but what the reg1 value will be assigned later on, it is the value of in1, right. And then in the what happens to the res2, the current value of reg1, it is not yet updated to in1, right. So, whatever is the current value of reg1, that is scheduled to be assigned to res2, but res2 value is still not updated, right. And in the next step, whatever is the current value of res2, that is assigned to res3, and the res3 value is not yet updated, and in the third case, whatever is the value of current value of res3, that will be assigned to out1, but out1 is not yet updated. Now, when at the end of the simulation, all these updates happen. So, in effect, what happens is that the current value of reg1, so this kind of structure will be synthesized to a shift register kind of thing. So, this register will correspond to reg 1, this register will correspond to reg 2, this one will correspond to reg 3, and this one will correspond to out 1, right. So, 4 registers will be created in this case, and the whatever the value of in 1 is, that will be assigned to reg 1, right, but it will be assigned when the clock edge comes, right, and what was the current value of reg 1, that will be assigned to reg 2 and so on, right. So, this is how it will be synthesized. Now, let us look at the when an always block is level sensitive, then how it is synthesized. So, when always block does not contain edges in the sensitivity list, then either combinational circuit elements or latches will be inferred. And when the value of the variable is updated in every possible paths in the conditional branches within an always block, then combinational circuit elements will be inferred. And if there is some path, if the variable is there is some path in the conditional branches where the variable retains its old value, then a latch will be inferred, right. So, let us take an example and understand what it means, right. So, let us consider this module top in which there are two always block. In the first always block, we see that out one variable is assigned a value of a when s takes a value 0 and assigned a value b when s takes a value 1. So, s can take either 0 value or 1 value, and in both cases either 0 or 1 either a or b is being assigned to out 1. So, out 1 is assigned in all conditional branches within the within the always block, and therefore, in this case combinational circuit element and specifically a multiplexer will be inferred. Now, let us look into the other always block. Now, in the other always block, if the enable signal is taking a value of 1, then out 2 takes a value of C, right, and if it is 0, then what happens? It is not specified, right. So, in that case, if enable takes a value of 0, then out 2 retains its old value, because it is not or the value of out 2 is not being refreshed or being written in that case when enable is equal to 0. So, it means that whenever in this block this always block is triggered and the value of the enable signal is 1, then out 2 will whenever the value of the enable signal is 1, then out 2 will get a value of C, otherwise it will retain its old value, right. So, we can consider this always block and the one shown here as equivalent, right. So, we write if enable is equal to 1 tick B1, then out 2 takes a value of C, else out 2 is equal to out 2, it is retaining its value, right. And if we if we draw a circuit for this, again it is an if else kind of structure, and therefore, a multiplexer will be inferred. It will the multiplexer will look like something like this, right. So, whenever enable is 1, right, whatever is at the D pin, at the C line, that will go to out. Otherwise, it will take the old value, and therefore, we have made a connection, a feedback, right. Now, this latch the multiplexer with a feedback is similar to a latch, right. So, this structure, this complete structure is nothing but a latch, right, a D latch. Remember that what is a D latch? So, if a D latch, just to recap what is a D latch, in D latch has a pin as D and enable and a third pin as Q. So, whenever enable is high, whatever is the value at D, that goes to Q, and whenever the enable is 0, then it holds the previous value, right. So, in this the description that shown in this figure is the same. If enable is equal to 1, then whatever is C that appears at out 2, otherwise it retains the old value, there is a feedback, right. So, corresponding to this module top, the two instances will be created. First for the always block, in which out1 is being written in all conditional branches, and therefore a multiplexer or a combinational circuit element will be in purely combinational circuit element will be inferred. And for the second always block, a D latch will be inferred. So, sometimes we actually want D latch to be or latch to be inferred because of the always block, but many a times what happens is that latches get inferred because of wrong coding, RTL coding. What happens is that latches often get inferred due to incorrect modeling of the combinational block. And what mistake we can make? We can inadvertently miss updating values in one of the branches of the case statement. Suppose we are writing a code for an FSM or a stay or some RTL code in which there is a complicated case statement, right? So, a case statement in which the select line is say of 8 bits, and based on the value of the select line, various operations are being done, right? And we wanted this case statement or case block to be inferred to a purely combinational circuit element, but because we missed some of the case statement, a latch will be inferred, because whenever for the cases where we have missed the assigning value to the to a variable, it implies that it will retain the old value, and therefore a latch will be inferred, right? For example, consider this code. In this code, we have in1 is on the select line for the case statement. Now, it has got 2 bits, right? So, there are 4 possibilities 0 0, 0 1, 1 0 and 1 1 for the signal in1, right? Now, for 0 0 we are writing the value of out1, for 0 1 we are writing the value of out1, and for 1 0 we are writing a value of out1, but for the case 1 1 we have missed writing a value, right? That may be a mistake, an inadvertent mistake while writing the RTL code, and therefore, in this case a latch will get inferred. So, to avoid such problems, what we can do is that we use default statement. So, whenever there are complicated cases, at the end we also case statement, at the end of the case statement we also write default, and for example, and then we write out1 is equal to say 1 tick B0. So, if we use a default statement, then for the case nothing matches in the earlier branches, it will fall back to default and the variable will be updated or refreshed, and therefore, a combinational circuit element will be inferred rather than a latch. Other thing we can do is that at the beginning of always block, we assign the value of the signals to a default value. For example, we can write out1 is equal to 1 tick B0 before the case statement. So, whenever the always block is triggered, out1 will be assigned one value, right? Of course, it will be reassigned later on down the code, but it will in the all conditional branches, if in the conditional branches we are missing the writing value to the signal out1, then this the value of out1 that we have written at the top of the always block, that will be come into action, and a combinational circuit element will be inferred rather than a latch. So, to know more into what we have discussed in this lecture, you can refer to this book. And just to summarize what we have done in this lecture. So, in this lecture we have looked into the RTL synthesis. So, we saw that RTL synthesis consists of various tasks. For example, first the parsing of the RTL code is done, then the elaboration is done, then we translate the Verilog construct to the corresponding logic gates, and then some optimizations are done. So, in the next lecture we will be looking at the translation of some more Verilog constructs, and we will also look into the optimizations that are RTL specific. Thank you very much.